Senger from Missouri State. Go ahead, Steve.
Hey, thanks. Well, very, very, very much thanks to all the organizers and Mel especially for putting this thing together. This is a gargantuan task. So really grateful to get to talk again. I love CANT. And this year is going to be no exception. I typically talk about Erdős type problems. So that's what I'm going to talk about again today. But point configuration problems. So this is upper and lower bounds on chains determined by angles, joint work with A.V. Paulson and Charles Wolfe. So I'm just going to give you basic setting, and then I'll tell you a handful of results. I don't even remember how many theorems we proved in this paper. It went up on arXiv a couple of months ago. But we have just a bunch of different results. So I'm going to give you a thin slice of those. So I'm going to use some slightly non-standard notation. If x and y depend on some integer parameter n, I'm going to use x squiggly less than y basically in lieu of big O. If we have x less than y and y less than x, then we're going to say x is squiggly equal to y. This just varies multiplicative constants. Many people have seen this notation before, but different people use it slightly differently. So the big motivation for this is the Erdős unit distance problem. I think about this problem literally every single day of my life. If we define u2 of n to be the maximum number of times that a distance can occur in a set of n points in the plane, then Erdős conjectured in 1946 that this should occur no more than a constant times n to the 1 plus epsilon for any epsilon positive. Now, the best we know is that it can occur no more than n to the 4/3. I want to quickly convince you this is a non-trivial problem. If I arrange 3 points in the plane, it's possible that they all have the same distance in between. But as soon as I put a 4th point down, no matter where I put it, try as I might, there's going to be a new distance introduced. So the idea is as n grows very, very large, we're going to introduce so many points that we're not going to be able to make all of them be a unit distance apart. And this is not seen in general. This has not seen any movement since 1984, the statement of the problem in the plane. So this is really the motivating problem. There are numerous variants of the problem, and I'll talk about a lot of those in the talk today. But everything in my mind comes back to I have a set of points somewhere, and I want to count how often does a particular configuration of those points occur. And one simple configuration is a distance measured between a pair of points. All right. Well, we can then use u3 of n to denote the same thing in R3. So the maximum number of times that a particular fixed distance can occur in a set of n points in R3. And the conjecture is n to the 4/3, with the current best result being just under n to the 3/2 due to Josh Tsal in 2017. Again, really challenging problem. So it's really hard in 2 dimensions, also hard in 3 dimensions, completely trivial in 4 dimensions. So in dimensions 4 and up, I say it's trivial because we can have up to n squared unit distances in some set of n points. And which set? Well, there's a counterexample due to lengths, which essentially takes n over 2 points on the unit circle in the first 2 dimensions, n over 2 points in the unit circle in the next 2 dimensions. Here's a handy picture. And the distance from any point on this circle to any point on this circle will be the square root of 2. So here I have a particular distance occurring roughly n squared times, n squared over 4, I guess. So numerous authors have taken this type of definition and run with it and said, well, if instead of looking at a single distance measured between a pair of points, let's look at many distances measured between many points. So if I have a set of k plus 1 points and I'm considering the k distances between those points, that's what I'm going to call a distance k chain. Now I know this is not a talk about distances, but this is just the setup to get us into angles. So written out formally, I'm looking at a k tuple of points from some ambient space. I mean, typically I'm going to think about R2 or R3, but you can also study similar problems in other settings, like a vector space over a finite field with an appropriately defined notion of distance, etc. The lengths example, if we look at these chains, is going to give us the trivial n to the k plus 1 occurrences of a distance k chain. So if I fix a particular distance, then I can tune my lengths example so that I have repeated versions of that distance. If I want to do different distances, there are tweaks one can make. But this is just to say that the lengths example provides that the problem is trivial for distances in dimensions 4 and higher. If I add new notation, let this CK, C for chains, be the maximum number of occurrences of a fixed distance K chain in any endpoints in the plane, any set of endpoints in the plane. Then with A.V. Powelson and Adam Scheffer, this would have been 2017 and 2018, we showed the following, which essentially says you can get a set that has, in 2 dimensions, you can get a set that has more and more chains as K gets longer, but there's an upper bound. Again, I'm not asking that you take this too seriously. Shortly after we put this on, or maybe it was like a year after we put this on the archive, Franklin Kupovsky took what we had done here and they did it the correct way, which is essentially they took the tensioning mechanism we had, and rather than just tensioning the last couple of points against one another, they tensioned everything sort of evenly. They have this like information theoretical way of organizing all of these inequalities. Very beautiful paper. And this is essentially tight, except in the case where K is congruent to 1 mod 3. And that's going to be when that's going to be like the unit distance problem is when K is equal to 1. So anytime that K is congruent to 1 mod 3, we're gonna have some sort of a loss. Again, I'm not too worried about these exponents for today's talk. I just want to give you concrete evidence that people have been studying this. There are results. Yeah, like I said, both are sort of inductive bootstrapping. You prove for a few small cases of K, and then you bootstrap. Another type of problem that people have studied, and I'm sort of leaning a little bit more heavily on this after watching Misha's talk. So after I saw Misha's talk this morning, Misha Rudnev, I sort of modified my talk to make it fit more with the day. So people also study these Erdős type problems with dot products. That is, how many distinct dot products are determined by a point set, or how often can a particular dot product occur. Now, we're going to typically avoid 0 dot products. And that might seem mysterious, but already in 2 dimensions, the 0 dot product question without further restrictions becomes trivial. And if we just look at dot products in general, so not just 0 dot products, but let's say non-zero dot products, this problem becomes trivial in 3 dimensions. So the dot product problem on its face is kind of falls flat. So you want to put some restrictions on it. But again, if we look at dot product chains, there are some interesting things one can say, and I've detailed that in other talks. But again, this R3 example can give us the trivial number of K chains. Last year at CANT, I spoke on more general configurations. So instead of just I'm looking for a K tuple of points, a path, I might be looking for something like this, where I have more general graphs describing the point configurations. This past semester, I've done some undergraduate research or research with undergraduates involving sort of a mix of distances and dot products. There are funny things that come up in each case that somehow come out in the wash if you put them together in certain ways. And also I've done with undergraduates recently in the last year or so, analogous results in vector spaces over finite fields and the modules of rings of integers ZQ. My master's student is looking at Galois rings, and it's fun. It gets intense. Okay, so what does this talk about? So I'm not quite 10 minutes in, so I'm not quite to the halfway part. You should at least see something about the title by the halfway part of the talk. So I'm sliding in sort of under my arbitrary rules. I'm gonna use this notation to determine an angle. If I have 3 points X, Y, and Z in RD, and D at least 2, I don't want to talk about angles in 1 dimension. I'm going to let this angle bracket of X, Y, Z just denote the angle they determine. Okay. If I have a K tuple of real numbers and I'm going to put them between 0 and pi, I'm not going to think about angles greater than pi just because you can flip them over. An angle K chain is then going to be a K plus 2 tuple of points that has the K angles that I've talked about. And why is it a K plus 2 tuple? Well, if I had 3 points, that would determine 2 distances, but it's only going to determine a single angle. So if I want to determine, let's say, 3 angles, I'm going to need 5 points. We have only stuck to paths in this sense because it's a weird sort of, I don't know if you'd call it a directed hypergraph or something, but this one would be sort of difficult to generalize. So we've just stuck to paths or chains. But this is kind of the statement of the problem is if I have a large set of endpoints somewhere, how many angles could they determine? And this has been studied. And then our sort of generalization of that, then how, if I fix a set of angles, how often can I find a K plus 2 tuple of points that exhibits that set of angles in order? Now, this is different from previous settings. It's like I said, an angle requires 3 points, whereas a distance or dot product or many of the other functionals that have been studied in the past, like LP norms or the circles, the LP circles, require 2 points. So there's this fundamentally different issue. When you do these Erdős type incidence problems, it's typically like, hey, I'm going to look at a set of points and their incidences with this family of varieties. Cool. The problem here is that the incidences get weird because the points are kind of they're not really the elemental object that you would use for angles. Angles are kind of, well, they're defined by rays, right? So you kind of want to use lines as your fundamental element. So we're kind of going below what might be seen as a fundamental element to study the angles. This is not unique. Other people have done this, but it adds a unique flavor to the analysis. So I'm going to give you, similar to that CK notation, I'm going to give you some really nasty notation, and we'll suppress most of it in the future. But basically, capital lambda sub k of E semicolon this list of alphas is just the number of K plus 2 tuples in E that determine those angles. I know this is somewhat prohibitive. There are a lot of symbols, but we're really going to suppress whatever notation we can. We're frequently just going to write lambda sub k of E. Most of the time, I'm going to be specifying all the angles or right angles or something like that. So we don't say that too often in this talk, but just so you see it formally written out. Okay, so in 1992, Pach and Sharir showed that if E is a set of endpoints in the plane, then the number of times that a particular angle can occur is no more than n squared log n. This is sharp for some angles. It's not known to be sharp for all angles. So they can construct sharpness examples for certain angles, but not for all of them. Later, 2005, Apfelbaum and Sharir showed that for a set of endpoints in R3, no particular angle can occur more than n to the 7/3. This, both of these are going to come up, but this was basically, you'll see, this is a big one for us. It's sharp for right angles, but it's not known to be sharp for all angles. And I'll talk more about this, but we spent the bulk of our time trying to generalize this theorem. We probably spent 9 months just on this, trying to go to pairs of angles. And we got lots of special cases, but nothing that was in general stronger. So more on that in a minute. Here are the results. So I'll try to run these down in the next 10 minutes. 2 dimensions is not super interesting. If we have n points in the plane and a k tuple of angles, then we have this even odd thing. If you'll recall from the results that I showed you due to Frankel and Kupovsky and the results, the previous results due to Adam, Avi, and myself, those also broke down by some modular relationship on k. And so k modulo something. Here it's k modulo 2. And the reason for this is if I look at, if I fix x1 and x2, and then I fix x4, wow, I do know my letters, some of them. If I'm looking for this particular angle to occur, then it's got to occur along this line. And if I'm looking for this line and this angle to occur, well, then x4 essentially fix x, the choices of x1, x2, and x4 essentially fix our choice for x3. Now that gives us, you know, n to the, that gives us n cubed in the case of k equals 2. But when we're in k odd, we're still going to need to use that Pak-Sharir. Okay, so we can essentially Lego brick these together. So I can say, well, I've got this many occurrences of angles, and then if I fixed an angle, that fixes these 2 points. So I can skip and fix the next point. But it's you know, you don't have to see the whole picture, but it's fairly straightforward for 2 dimensions. This is sharp up to logarithms, as the following result will show. So if you give me a set of non-zero angles, then I can construct you know, angles in that range between 0 and pi. Then I can construct up to, you know, up to this log term, I can construct a set of points that exhibits this k-chain. And it's a pretty straightforward construction. I'm just going to put a bunch of points along a line, and then each of these points will come down at the appropriate angle to another line at the appropriate angle, and we get these sort of crooked railroad track things. Then I come down and whatever, as many steps as I need. Fairly straightforward construction, not super difficult. Required some thought. We worked on it for a little while. On to 3 dimensions. This is where everything got really challenging. So we patted ourselves on the back really hard. We were like, we're so smart. We've pretty much up to logarithms. We've sorted out most of what we want to know about 2 dimensions. Let's look at 3 dimensions. 3 dimensions already, if you just look at general angles, gets really, really, really hard. So if you, or at least it was hard for us. We look at the varieties that we have to consider are going to be intersections of cones and spheres, and those get weird. So we believed we had some results, and they were just really bad. So we restricted ourselves to right angles. So now instead of the special case of cones we were dealing with now is a plane. So planes and spheres intersect pretty regularly. Now our conjecture was that for k equals 2, so what's a 2 chain for angles? That's going to be, again, a set of 4 points with, and now we've prescribed right angles with 2 right angles. So that's going to look like this. Now in 3 dimensions, recall there's a lot more flexibility. So, you know, you can have something like this flopping around. So we don't necessarily know that this line is parallel to this line as it would be in 2 dimensions. After, like I said, about 9 months of work, so the 3 of us meeting over Zoom at least once per week, if not twice per week, we could not improve the trivial bound. And this is trivial because it's essentially Applebaum and Sharir gives us n to the 7/3, and then we have n to the 3/3 choices for our next point. So that is Applebaum and Sharir gives us n to the 7/3 choices for the first 3 points, and then just n choices for the last point. It's unfortunate, but this was the best we could do. Now we have a bunch of special cases, better results in special cases, but in general, that's the best we could do. However, if you go to longer chains, we do get some what I would call non-trivial results. So so here's, this is Applebaum and Sharir's result. This is single angles. This is our, like I said, trivial result. It does not really materially improve on Applebaum and Sharir. But once we get to 3 chains, 4 chains, and 5 chains, there's enough moving around that we can improve. And I won't go into all the details, but after we get up to here, then we have sort of a self-improving bootstrapping mechanism similar to the distance chains case. So once we get up to 3 chains, we can really split into cases based on whether points are coplanar or not. If a bunch of points concentrate in a plane, we lose some of the incidence bounds that we have, like point plane incidence bounds. But if a bunch of points are in a plane, then we have nice R2 bounds in that plane, and we can tension those against one another to get some gains. But this was where we really worked hard on the paper, and this was a whole lot of fun. Again, we probably got a dozen pages typed on this that just didn't make it to the final draft because they weren't really proving anything. This is just super special cases. So moving on, I do want to mention a couple of lower bounds, and then later I'll talk about pinned estimates, and then I will hopefully finish in time. So there are these lens type examples. So you remember the lens example for distances was the two orthogonal circles in R4 or higher. Well, similarly, Applebaum and Scherer showed that there's a set of endpoints in R4 forming n cubed right angles. So that's going to be trivial. Well, we can modify this to get a set of, in R5, to get a set of endpoints that give us n to the fourth right angle 2 chain. So this is trivial because, again, a 2 chain is going to be a set of 4 points. So we've got as many 4 tuples as possible. And then it gets even worse. In R6, we can form n to the k plus 2 right angle k chains. So there's sort of a looping mechanism that once you get into 6 dimensions, you can set up a cyclical thing, and then whatever k you'd like, you can construct a k chain. Moreover, this final result in R6, and so if you can do it in R6, you can do it in any dimension higher than 6 by embedding. This last result is also true for some more general angles. Again, I don't want to go into all the criteria, but for most of our higher dimensional investigations, we stuck to right angles because they were just easier to deal with. But in R6, we found a way to squeeze in some other angles. We also did some pinned results. So in some cases, we would look at chains that share a point. So how many chains share this same first point? So this would be called a pinned result. It turns out that in RD, so for any dimension 2 or greater, there exists a set of endpoints with n squared triples determining any angle we want that share the same middle point. So if I have fixed this middle point, it's pretty easy for me to just arrange endpoints on 2 lines sticking out, and then boom, I've got n squared triples. So not very interesting. However, if I have endpoints in R2 and any fixed angle, they're at most n to the 4/3 triples with an angle alpha starting from the origin. So now if I fix the first point and I'm looking at second and third points, the bound is n to the 4/3. So the takeaway here is it depends on which point you've pinned. Now, moreover, this is sharp. We can show it's sharp by modifying a Semer-Trotter sharpness example. So this is, again, echoing some of the things that Misha spoke about in his dot product. Okay. This is a repeat of the previous slide. No, it's not. Oh, sorry. I just wanted you to see what the definition of pinned was both times. So we also have set of endpoints in R3 forming n squared right angles. We have a whole bunch of these results. I'm just giving you a few of them. So yeah, and then in R6, we can again modify the R6 construction to get as many pinned chains as we'd like. So this is just to say that you can study these chains, you can study these pin problems for distances, for dot products. You can also study them for angles, and we've got a whole bunch of results. They're on the archive. I can't remember the name of it. It's something like chains determined by angles. Oh yeah, and this also holds for more general angles. Anyways, that is my talk. I want to thank you so much for your attention. And then I have a bonus slide. So the bonus slide is just because Misha brought it up. So I'm squeezing this in my last minute. He talked about this this conjecture involving distinct dot products. There's another way to phrase it, and I bring it up every CANT. So I wouldn't be coming to CANT if I didn't ask you about it. So if I have large sets of real numbers where G is essentially a geometric progression, and it's the same size as AA, this is a left turn. This has nothing to do with my talk, sorry. Then I claim that AA plus 1 times GG has to grow. I've been trying to prove this since 2009 to no avail. So open problem for anyone who wants to deal with it. You get nothing by using standard energy methods. So if you can use energy methods in a clever way, that's great. But with standard energy methods, you get nothing. But it's related to what Misha spoke about, and it would improve some things. So that's actually the end of my talk. Thank you.
All right. Thank you very much, Steve. Um,